Good morning, class, and you're welcome to today's study section 6, chi-square. What are the objectives of this study unit? The objective of the study unit are to understand the concept and application of chi-square distribution in statistical inference, learn the use of chi-square goodness of fit test to determine how well observed data fit an expected theoretical distribution. Apply the chi-square test of independence using contingency table to analyze the association between categorical variables. Interpret the result of chi-square test in real-life context such as business, social sciences, and health studies. Recognize the assumption and condition under which chi-square tests are valid. Example like a large sample size, expected frequency, and distinguish between goodness of fit test and test of independence and apply them appropriately. That is, when you use them, develop skills to compute test statistics, compare them with critical values, and draw correction. Learning outcome for study section 6 unit 3. By the end of this unit, students should be able to 1. Define and explain the chi-square distribution and its application. State the assumptions and conditions necessary for applying chi-square test. When do we apply it? What are those assumptions that we have to in before we can apply chi-square test? Formulate hypothesis and carry out a chi-square goodness of fit test to check whether observed data conform to a theoretical distribution. Construct and analyze contingency table to test the independence of two categorical variables. Compute the chi-square test statistics and determine the corresponding degree of freedom. Use critical values and p-values to make decisions about hypotheses in chi-square testing. Interpret the results of chi-square tests in meaningful real-life context and differentiate between goodness of fit and test of independence. Introduction. In many real-life situations, the data we collect are categorical rather than numerical. Example of a categorical data, I think when we are in a study section 1 unit 1, we discuss about different types of data. We discuss about interval data, ratio data, something like that, and then we mentioned something like categorical data. Example of categorical data is like, let me say, the gender of people. Under gender, we can have male or female. That is category. That either they fall in the male category or female category. So, for example, we may want to know whether customer prefer different brands of a product. That's an example. Whether student performance is related to gender or whether a die is fair. To analyze such categorical data, we use chi-square test. That is the type of test that we use in analyzing categorical data. The chi-square distribution is a family of probability distribution. I think like when we are in study section 4, we'll talk about probability distributions, if we can remember. So a chi-square distribution is also a family of probability distribution that is widely used in hypothesis testing, particularly for categorical data. It is always positive and depends on the degree of freedom, which are determined by the sample and the test. There are two main applications of chi-square test. The first application is chi-square goodness of fit test. What does that one do? It checks whether the distribution of observed data matches a theoretical or expected distribution. Example, when we are testing whether a die is fair, each face equally likely. The second application of chi-square is when testing chi-square test of independence, which is our contingency table analysis. What do we use the chi-square test of independence, that is our contingency table analysis, to do? We use it to test whether two categorical variables are related or independent. Example, testing whether smoking habits are independent of gender. In statistics, many research problems involve categorical data, that is, data that are classified into categories rather than being measured numerically. I've told us that our gender, we can't measure it numerically. It's a categorical data which is either male or female. Example of categorical data: example, do students prefer online or face-to-face learning? It is in categories. We can't measure them numerically. Another example is, are exam results independent of gender? That is another examples of categorical data. Is a die fair? Is another example of categorical data. For such cases, we use chi-square test, which are based on chi-square distribution. And what is chi-square distribution? The chi-square distribution is a continuous probability distribution. One, it depends on degree of freedom, and it is always positive and skewed to the right, though it becomes symmetric with larger degree of freedom. Those are the properties of a chi-square distribution. The chi-square distribution is a continuous probability distribution. Another property is that it depends on degree of freedom, and it is always positive and skewed to the right, though it becomes more symmetrical. When they say something is symmetrical, like a normal distribution is symmetrical because it has a bell shape, and it becomes more symmetrical with larger degree of freedom. When the degree of freedom is much, the chi-square becomes more symmetrical. What are the assumptions of chi-square? They are: one, the sample is random. The sample is random. Another one is the data are categorical. Expected frequency in each category should be at least 5. That is the rule of thumb. And observations are independent. No individual counted in more than one cells. Those are the assumptions of chi-square. Now, the second one is chi-square goodness of fit. The chi-square goodness of fit is used to compare the observed frequency and the expected frequency from a given theoretical explanation or phenomena under investigation. We use it to test whether an observed frequency distribution matches a theoretical distribution. And I told us in study section 6 unit 1 in hypothesis testing, statistical inference, that we have to set some, when we want to perform statistical tests, we set some hypotheses, where I think I discussed about null hypothesis and alternative hypothesis. So here, our hypothesis, which is our H naught, which is our null or true hypothesis, is that the observed frequency follow the expected distribution, while our alternative hypothesis, the observed frequency do not follow the expected distribution. The formula for our chi-square, the formula we use for chi-square goodness of it is chi-square is equals to summation O high minus E high all square all over E high, where our O high is the observed frequency, our E high is this expected frequency. So the formula for chi-square is summation O high minus E high all squared all over E high. The statistics defined above has an approximate distribution with degree of freedom equal to 1 if the expected frequencies can be computed without having to estimate population parameter from sample statistics. That's when we use the formula I've mentioned earlier. Another one is if the expected frequency can be computed only by estimate, which is estimated in the population. Example, the distribution of final grade given by STS202 lecturer in the past was 10% A's, 20% B's, 30% C's, 250% D's. A new lecturer gave the following grade for the second semester. So from here, category A, our observed is 12. For category B, our observed is 20. For category C, our observed is 26. For category D, our observed is 14. and for category F our observed is 8. If you also check from the questions, the distribution of final grade given by STS lecturer in the past was 10, that is the observed, 10%, 20%, 30% for category C, 50% for D, 15% for F. So when they ask us to that, is there any significant evidence to suggest that the new lecture policy is different from that of the former lecturers? Use a 95% level of significance. We said we should use take our alpha to be 95%. First thing, we set our hypothesis. They said H naught given P1 is equals to 0.10. How did they get that 0.10? 10 divided by 100, it will give us 0.10. 20 divided by 100, it gives us 0.20. 30 divided by 100, 0.30. Then we do for others. Then H1, which is our alternative hypothesis, is that our H naught, it is not true. What is our N? Our N will be 12, that is our observed. 12 plus 20 plus 26 plus 14 plus 8, which give us, then we estimate our expected frequency. Our observed is given, then we calculate our expected frequency. So our expected frequency is 10 over 100 times 80. Our 10 is given in the question, divided by 100, which is 0.10 times 80. That will give us 8. The second one is 20 divided by 100 times 80. That will give us 16. Then we do for others. Then we now bring our formula, which is chi-square calculated, which is equals to summation I ranges from 0 to 5, observed frequency minus expected frequency, all squared all over expected frequency. So we do for each sample, each observation, that is for 12, that will be 12 observed frequency minus 8, which is our expected frequency, all squared all over expected frequency, plus observed frequency for category B minus expected frequency for category B, all squared all over expected frequency for category B. Then for category C, it will be observed frequency, which is 26, minus expected frequency, which is 24, all squared all over our expected frequency, which is 24. We'll do for the rest, and our chi-square at the end of your calculation, your chi-square calculated will be 6.3. Since there is percentage class grades, then we estimate our degree of freedom. Our degree of freedom is k minus 1. That is how many columns? We have 5 columns. That is our k. Our k is 5 columns. How many columns? How many? 5. A, B, C, D, and E. That is our category, is our k. So it will be k minus 1, which is 5 minus 1. That will give us 4. And our alpha is 0.05, 95%. That will be 95 divided by 100. That will give us 0.95. Then 1 minus 0.95. That will give us 0.05. Then we check our table. We have, in our statistical table, we have our chi-square table. We check for our chi-square value at 0.05, 4. That is giving us 9.49. Then we make our decision. We reject H naught if our chi-square calculated is greater than chi-square table, that is our chi-square tabulated. Otherwise, we do not reject. From here now, our chi-square calculated is 6.3 and our chi-square tabulated is 9.49. So from here, since our chi-square calculated, which is 6.3, is less than our chi-square calculated, which is 9.49, then we conclude we do not reject H naught. Since we are not rejecting H naught, we make our conclusion from the hypothesis that we set. Then we conclude that the data do not suggest that the new lecturer grading policy is different from the former lecturer grading. Also, the second test is the chi-square test of independence, which is our contingency table. What do we use it for? We use the chi-square test of independence, our contingency table. We use it to test whether two categorical variables are independent. We use our contingency table, that is our chi-square test of independence, to check whether two categorical variables are independent. Contingency table uses the statistics randomly by selecting items. They are classified into two different criteria to determine whether some protective measure or sample preparation techniques have been effective or not. Instead of using table in the goodness of it, we will have a two-way classification table, or table in which the observed frequency occupy H rows and K columns. Such tables are called contingency table. The expected frequency, which is computed subjected to some hypothesis according to the rules of probability, is based on the observed frequency. We set our hypothesis that our null hypothesis, that is H or not, or the true hypothesis is that the variables are independent. Then our alternative hypothesis, that is the variables are associated, not independent. Formula to estimate our expected frequency: EIJ for test of independence is row total times column total divided by grand total. Let me repeat myself again: row total times column total divided by grand. So this is the formula. Chi-square equals to, since we are considering row total, column total, we have two summation. Summation I ranges from 0 to I ranges from summation I ranges from 0 to half, that is for row. Then summation I ranges from 0 to C or N for column, and to brackets OIJ, that is the observed frequency minus EIJ, which is our expected frequency, all squared all over EIJ. Now our degree of freedom will now be row minus 1, column minus 1. The other time we consider row minus 1, but here we will consider row minus 1, column minus 1, where our R is the number of rows and our C is the number of column. This is an example of a contingency table. We have our row 1, row 2, like that, and we have our column 1, column 2, like that. So we sum the total of the row, we sum it row wise, then we sum it column wise, then we come to our grand total. We sum it, let me repeat myself again, we sum our observed row wise, we sum it column wise, then we estimate our grand. Example, we have our test statistics, that is the formula we are using, and we have our degree of freedom. Example, they said consider the case where pressure gauges are being hydraulically tested by 3 inspectors prior to shipment. It has been noted that the acceptances and rejection for some period of time have been as follow. We have inspector, which is our column, and we have passed, failed, or passed or failed as our row. If we sum it column wise, which is our inspector, we have 150 plus 20, that will give us 170. We have 50 plus 10 column wise, that will give us 60. We have 130, that will give us 130. From here we can see that we have 3 columns. Then if that is inspector, if we sum it row wise, passed, which is our row 1, we have 150 plus 50, making 200 plus 100, that will give us 300. We have failed, 20 plus 10 plus 30, that will give us 60. So if we do our total, 300 plus 60, that will give us 360. 170 plus 60 plus 130, that also will give us 360. If we sum it, all our row total, when we sum it together, it must give us our grand total. All our column total, when we sum it together, it must give us our grand total. That means the row total must be equal to grand total, or the column total must be equal to grand total. Now they said we should test the hypothesis that all inspectors are equally stringent, take alpha, that is our alpha to be 0. So here we set our null hypothesis and our alternative hypothesis. Our null hypothesis, which is the true hypothesis, is that all inspectors are equally stringent, while our null hypothesis, our alternative hypothesis, is all inspectors are not equally stringent. So here, this is the formula, our test statistics that we are using for chi-square test of independence or contingency table. Now, to estimate our expected frequency, which is our Eij. Eij equals to E11. E11 means row 1 column 1. Then what is the row total? The row total for row 1 is 300, while the column total for row 1 column 1 is 170. Row 1 is 300, the row total, and the column total for row 1 is 170. Therefore, to get our Eij, which is our expected frequency, it will be 300 into bracket times 170 all over our grand total, because if we could remember, we said in order to estimate our expected frequency, it is what? Row total multiplied by column total all over grand total. So for E11, this is row 1 column 1, our row total is 300 times our column total, which is 170, all over our grand total, which is 360. That will give us 141.67. Then E12 means row 1 column 2. The total row total for row 1 column 2, row 1 is 300 and column 2 is 60. For column 2 is 60. That will be 300 times 60 over 360. That will give us 50. Then for row 1 column 3, it will be what? 300 times row total, 300 times column total, 130 divided by our grand total. That will give us 108.33. We do for E21, which is row 2 column 1. Row 2 column 1, row first before column. So row 2 column 1. The grand total for row 2 is 60 and the column total for column 1 is 170 divided by 360. So when we multiply it together and we divide it by 360, that will give us 28.33. Then we do for E22, which is row 2 column 2 divided by row 2 total and column 2 total divided by grand total. That will be 60 times 170 divided by 360. Then we do for E22, row 2 total multiplied by column 2 total divided by the grand total. That will give us 10. Then we do for E23, that is row 2 column 3. That will be 60 for row 2 total times column 3 is 130 divided by 360. That will give us 21.7. If you see from here, E1 to E11, from here we have row 1 column 1. This, the first one is row 300 column 2, row 1 column 2 300, row 1 column 3. If you see from here, 300, then row 1 column 1, column 1 is 170, column 2 is 60 for E12, and for E13 is 130, 1 column 3. Then after estimating this, then we now use our chi-square formula, that is double summation. I ranges from 1 to half, I ranges from 0 to column. Eij, Oij minus Eij all over Eij. Oij minus Eij all squared all over Eij. So from here, observed for row 1 column 1 minus expected for row 1 column 1, the new expected that we estimated, all squared all over expected frequency of row 1 column 1. We do for row E12 also. We apply our observed for column 1, row 1 column 2 minus expected for row 1 column 2 all squared all over expected for row 1 column 2, which is our E12. We do for E21, that is, will be observed for row 2 column 1 minus expected for row 2 column 1
all squared all over expected for row 2 column 1. Then we do for E22 and we do for E23. After calculating all this, our chi-square will now be 6.7817. Then we look for our critical value. Our critical value, I think we are given 95%. 95 divided by 100, that will give us 0.095. 100 minus 95, we first divide by 100. 95 divided by 100, that will be 0.5, then 0.05. Then we take our row, how many row, then how many column, take away 1 from it, that is 2 row, 2 minus 1, and how many columns, 3 columns, 3 minus 1. Then we check this in our chi-square table, it will give us 5.99. Then decision, our decision is that we reject H naught. If our chi-square calculated is greater than chi-square table, we reject the null hypothesis, which is our H naught. So from here, since our chi-square calculated is greater than our chi-square table, which is our 5.99, that we get this 5.99 from our statistical table chi-square. So the null hypothesis is rejected, and we conclude that some inspectors are more demanding than others. Then I want us to go and read about what is goodness of fit test used for. What is goodness of fit test for?